All right, so our goal today is to talk a little bit about one-dimensional motion, which is chapter 2 in the workbook. So chapter 2 in here, chapter 3 in OpenStax. Most books actually have those switched the other way, which is the reasoning for the order. So we're going back to hit chapter 2 now. All right, so let's go ahead and get right to the beginning of this thing. Oops. And so some of this might be a little bit weird since normally I do things a little bit differently in a real class. So this is a little bit crazy. So you could look at this while I get a file up, and I'm looking at page, it looks like 21. So everybody can bring that up, and I'll try and bring this up as well. Give me just a second. A little discombobulated today for some reason. I don't know. Forgot to open up the workbook PDF. So that's what I'm doing right now, and the solutions just in case. Sorry about that. All right, now I got that going. And so let's go to here. Now I could share screen so we've all got it together. And let's see. Okay. And I'll get to the chat in just a sec in case that was something there. Come on now. Okay. There we go. And so this is our kind of our definitions that we're going to be using for 1D motion. So hopefully after this class, you can go and read the textbook and kind of add in another layer of understanding these definitions. But one of the things that we've got to watch out here, one of the more common things that can trip students up is we see that there's a difference between position, displacement, which is a change in position. Notice that delta symbol appearing. And then distance, which looks the same as displacement, but it's totally different. There's no vector. And so I guess I wrote that, I tried to emphasize that by saying this is a scalar. Similarly, students also really want to watch out for the difference between velocity, both of these are velocities, and notice that's a vector, versus speed. All right. And so this is why I like to cover chapter 3 first, usually, because we've discussed vectors and you already have this concept of magnitude versus vector versus maybe a scalar, etc., a little bit. And so hopefully that will actually help us when we're talking about this. So now in this case, let's go to a simulation really quick since I can't do what I normally do. Let's see if this simulation works. So this is what I thought might work. Come on, screen. I got it right here. I forgot to do this. Oh, it's still loading. What's going on here? Oh, no. All right, so maybe my simulation is a little slow here. Sorry about that. I thought I had opened this up a few minutes ago so it would have plenty of time to open, but sorry about that. Okay. And so the idea here is hopefully you can see this, and I know there's computer lag, and I think I've got my cable in here. So if you want to explore this on your own, you can, Jay, can you find the link for this online? Just do a Google search for the Moving Man FET and find that and give that to them. And that way they can play with this on their own. So thanks, Jay, for doing that. If you can't find it, let me know. But the idea here is we could pick an initial position here. We could pick an initial velocity and maybe even an acceleration like this. And then I can run this thing and see the behavior of this motion. Now we're going to be doing a really simple case. So this person here is only going to be moving left and right. All right. So they're going to be moving back and forth in different ways. So let me clear my drawings out of there. And let me see. Thanks, Jet. Thanks, Jay. All right, so let's go ahead and run this thing and just see what happens, right? So if we do this, we notice that in this particular case, as time goes on, I don't know how much this is lagging on your machines at all, but we see that the position and the velocity are changing, but notice the acceleration is held constant here. And he's probably going to crash into the wall any second now. All right, and so that's great. Now, so let's go ahead and call that. So what we want to do is, before we could really explain anything moving around in 3 dimensions, we've got to understand this simple problem. How do we analyze and describe and write equations that help us analyze that thing's motion right there? Just something simple like that. All right, so we're finally getting into something that's kind of hinting at physics here. So let's take a look on the board and see what we can do here. All right. So where did I put those markers? Okay. So it turns out there's going to be some equations that model this. There we go. And one of the more common equations might be this equation. Delta x equals v initial x times time plus 1/2 a sub x t squared. Now, you might be wondering what this is. I'm going to try and explain these variables using the definitions that are on page 21. In particular, this doesn't really, you don't see any vectors here. And so you might be wondering why I mention all this stuff about vectors and then I immediately write down a question that's not a vector equation. It turns out this is a vector equation, and I'm going to explain that right now. Really, each of these should be a vector component. Now, the reason I'm writing the x's on everything is because later on, when we have 3D motion, it's very easy to change this equation to y by just changing letters to y, or z. So I want you to get in the habit of using these subscripts to keep track of which variable we want to talk about. In this case, delta x is the displacement. And I'm going to underline that letter P, displacement. It is not distance traveled, it is displacement. And that's x final minus x initial. It's a change in position. We're going from the initial state to the final. All right. Now, in this case, if we're doing everything in 1D motion, I think you could probably agree that the vector component is 0 in the j hat and 0 in the k hat. So we expect, for the problem that we just looked at, the guy walking back and forth, we expect 0 in the j hat and k hat. So I could actually write this as x final, x initial, with a minus sign here, in the I hat. Similarly, everything up here in this equation, right, for something that's just going left and right, we know the entire vector is just in the I hat. So what I'm going to do is I'm going to take this equation up here and rewrite it by replacing all the red vector arrows with an I hat. Okay, so we have delta x in the I hat, just like right there. We said delta x is a vector. Well, I know it's basically this amount in the I hat, where this could be positive or negative. Next, we have v initial x, also in the I hat, right? The velocity, left or right. V means velocity here. So I'll write down what this means. This is initial velocity, not speed, velocity in the x direction. Okay, we're getting low on the board there. Times time, t is time. Let's maybe write this out. Plus 1/2 a sub x. Again, in the I hat, there's some acceleration vector left and right. I'll explain more about what that means in just a second. If you want, it's something like, let's say, approximately equal to It's like the change in velocity over the change in time. More on that in a minute. And then we get time squared here. Now, physicists are notoriously lazy when they get all these variables, all right? Let me see if I can get a little bit more light on here. All right, so that's just kind of, I don't know, having trouble with the lighting today. Let's just keep it like that. All right, so in this case, I do want to point out, because physicists are so lazy, what they'll do is they'll be like, well, whoops. Let's just cancel all these I hat terms. Which gets you back to the original equation I wrote, which had no arrows up here. If I cancel all the I hats out, I basically get this result. What is weird about this is now as a physics student, you're now expected to know, even though there's no vector there, you should think of it like a vector and think, oh, is this going to the right? If so, I put a positive number. If it's going to the left, I would put a negative number. This one is a velocity, not just a speed. So if it's going initially in the x direction to the right, I'd put in a positive number. If it's going to the left, I'd put in a negative number. Same thing with acceleration. So if I could go back to the sim here. Oh, and let me check the chat. The subscript on the A is an X. Sorry about that, Dom. Yep, all those are X's. Yeah. Sorry about that. And thank you for catching that, whoever did. I think that was Amy maybe or something. I don't know. Let's go back to this. Oh, whoops, I forgot to screen share. Come on. So in this particular case, remember this person, if I could play that, oh, zoom, come on. If I could play this back, if it lets me, notice this person actually starts right here. So notice its initial position is about negative 3.5. So here, x initial vector would equal negative 3.5 I hat for this particular case. No one would ever write that because everyone's lazy, and you're going to get lazy too. So everyone would write x initial equals negative 3.5, and I should be careful. That's still wrong on both of these. What did I forget on both of them? Units.
Units.
Yep. Thank you. So there we go. So the idea here is this is the right way to do it. But everybody, including you, and every physics book I've ever read does it this way, where we just assume you know that we're talking about vectors. Is that a good thing or a bad thing? I don't know, but it definitely helps you get the problems done faster, but it definitely makes it harder to learn at the beginning because it's more confusing. So 6 of one, half a dozen of the other. If you want to include the arrows on there and the I-hats, that's fine, okay? But you'll see in the solutions I never do. I just do the same thing as every other book. Let me pause for a second and see if there's any questions about that. Any questions so far? You can just unmute or throw it in the chat either way.
So both ways are fine?
Yes. Both ways
Okay.
are totally fine. Yeah. Let's do this too while we're at it. Oops. I should have drawn that position in blue, shouldn't I, to color code it? See that? They use blue down here. Oh, well. Let's clear all my drawings. I'll redo that. So we said X. Oh, geez, come on. X initial equals negative 3.5. So that's where I got that. I'm writing this down because as soon as I hit play, we're going to lose it. Now, in this case, the velocity initial in the X is about 4, right? Oh, whoops, it's red. Come on. Jeez. This would be so much faster in a real classroom, but what are you going to do? Is about +4, right? Meters per second. And again, you could stick the I hat on in the vector, but nobody's going to do that. Finally, in this case, acceleration is the green one. A sub x is equal to, what is it? Negative, I think it was negative 3.3 or so. Now, what are the units going to be? If you could see my screen really quick, I don't know. Well, oh, it's right there for you. Remember, it's velocity over time. So velocity has units of meters per second divided by seconds. That's where we get this meters per second squared down here. So that's why this one has units of meters per second or meters per second squared. Sometimes you'll hear that either way. Now, when I run this thing, none of these are going to change. This is the initial position. That is not changing. The position is changing, but the initial position is not changing. And if I keep coming closer to the screen, maybe you'll remember. All right, so maybe not. In this case, the initial velocity, again, this is not the velocity at all times. It's just the starting point. That is not going to change. So, and the acceleration in this case is also a constant. So these three things are constants in this code. And then everything else is going to be generated off of that using the equations that we're talking about. So finally, if I play this again, right, those initial values are not changing, even though the man's position is changing and the velocity is changing, the initial values are not. And so there we go. We could see all this. This guy's going. Let's speed this up a little bit. There we go. Run it a little faster. Okay, great. Now, in this case, again, I want to point out in this equation here, we see that this is a constant. This is a constant, but time is something that's changing, right? The time is evolving. As a result, this is changing. Now, keep in mind, this change in position is related to the initial position. So this part is also a constant, and the final position is what we're actually seeing the man as he moves around. This is the thing that is affected by time and the initial conditions. So in this case, if I could, x initial, a sub x, and v initial x are all constants. As the time changes, we see the final position changes. And then we're seeing position as a function of time. So yeah, another way to think about this, as a kid, you probably learned distance equals rate times time. That's true on average. This is the next level up. Think about this. This is a lot like distance. It's not exactly the same, but distance is equal to rate, how fast you're going, times time. But if you're accelerating, this helps you account for the change in the rate. So all this together is basically a stronger version of distance equals rate times time. Okay, and it's valid when it's moving in more than one direction. It could be moving right or left, so or up then down. So this displacement is not exactly the same as distance, and we'll get into that next. So let's see here. All right, any questions on that? Let me get to the gallery view so I can see. Is this making any sense? Any thoughts? All right, so far so good. Yeah. So let's go back and see if there's anything else I really wanted to mention on this definitions page here. Okay, so it says you can see my screen. Can you guys see that all right? I hope so. It's weird. It's not, it's doing some quirky things today. My Zoom is. It's not putting the green border on, but thank you, Edgar. Okay, so let's take a look here. We've talked about, we started talking about this stuff right here, right? So even though this looks like it is a scalar equation, it is actually a vector equation because all the I-hats drop out, all right? So I just wanted to be clear on that. In this case, if you know calculus, that's great. If not, we'll talk about this in 161. So this is probably the biggest one we should talk about here. Distance. Distance is really important to talk about. You usually want to know how far something traveled. It turns out something's displacement is not the same thing as its distance It is in some cases, which makes it extra confusing. For example, in the case of this guy walking back and forth, let me just show you this. So, and let's go to here and to me. All right. So I'm just going to simplify that animation that we just saw with a red line on the board here, or what was it? Blue was position, I think. So in this case, the guy started right here, he went this way, and then he came backwards, and he hit into the wall. Now in this case, X initial, I think, was negative 3.5. And I can't remember exactly, so I'm just going to check really quick. I think the final was negative 10, yeah. So X final here, and I don't know if you remember, he almost made it to the origin, or X equals 0. So in this case, I just want to point out the difference between distance and displacement in this case. Now think about this. How far did this guy go? Well, this is 10 meters, right? And this distance right here is 3.5 meters. So the total distance is 13.5 meters. Fine. In this case, the displacement is this. And you have to remember, just a sec. This is what I've been saying all day, is there's this implied I hat on these. So nobody writes it, but we know that there's an I hat. That means we have to include the plus minus signs. That's essentially what this means. So let me say that too. So much of physics at the beginning is getting your signs right. Okay. So in this case, let's just work it out. X final is negative 10 meters minus negative 3.5 meters, which is going to be what? Negative 6.5. Hopefully I didn't screw that up. But the idea here is I do want to point out that distance is not just the absolute value of displacement. That said, if an object never reverses direction, then distance and displacement are related by absolute value. So check this out. If this object reverses direction, the green distances will never equal the blue displacement. But if it only goes to the left or only goes to the right, basically as long as it moves monotonically or in only one direction, then you could say distance is the absolute value of displacement. In a lot of physics problems, things only move in one direction. So students get really sloppy and lazy, and they start using the words distance and displacement interchangeably. I will do that as well on a problem where they're moving in the same direction. So we all have to be careful whenever it's reversing direction. I don't ever want to say distance and displacement interchangeably because they're different numbers and they mean different things. That's one of the trickier parts I wanted to stress here. How is that going? Is that making any sense? Some. Right on. And so, and like any physics class, you're never going to know anything until you start doing some problems. So maybe we should start doing some problems together. And then at any time, I realize this is a goofy class online. So if there's something that doesn't make sense to you, just ask right away. Our goal for this chapter is to first do some simple problems with math to kind of get you a feel for it. Then we're going to do some simple problems without numbers, use letters instead, because that's a stronger technique that helps us get closer to coding and real work. And then we're going to start talking about graphs. So we'll do all of those in this, and this is a really big chapter. So yeah, let's go ahead and get started. Give me a sec here. Let me show you some other equations and some definitions. You're going to want to read after this class, all right? So give me just a second here. All right, so we've talked about the definitions a bit. give me just a sec. This chart in here, I will talk about this more once we start doing graphing. So that's going to be maybe 2 days away. So maybe next Wednesday or next Monday, end of class, something like that. So you can ignore that for right now. And then down here, I hope I just stressed this one. Be careful when an object reverses direction. So basically, you could be sloppy all you want as long as the object doesn't reverse direction. As soon as it starts reversing direction, we got to be careful, okay? The same thing that I said about displacement will also be true for average velocity and average speed, right? Distance over time is going to be average speed, whereas displacement over time is going to be average velocity. And we see that when you reverse direction, distance and displacement are not exactly the same thing. They're not even related by an absolute value. So we have to be careful with velocity and speed when an object reverses direction. Okay, I cannot stress this part enough. The equations we're about to talk about, these equations like this one that I just showed you, and then all of these subsequent ones here, they are only valid if acceleration is constant. And you may think, boy, that's pretty limiting. But it turns out in practice, if you have a problem that is non-constant, you write a computer code and you have the computer code slice it up into tiny sections where acceleration is approximately constant. So it turns out these are hugely valuable, even though it seems initially limiting. All right. I mean, it's a big deal, right? We can handle objects with a force on it using these equations. And so that's pretty useful. Some different notations here. These are the different ways you'll see it in different books. I want to point this out. V initial x, sometimes people use V0x for velocity at time 0. Notice this other one, V final x. V final x is sometimes just written as Vx. Why? Because that is the thing's velocity in the x direction at some random time t. If you're curious, we described this. This is how we could figure out the object's position as a function of time. Notice here, all I did was I moved the initial over to the other side. And so when I do that, this is basically the equation that computer was using to compute the little guy's motion as he moved back and forth. Similarly, this is the equation to get the speed. Oh, sorry, I just misspoke. The velocity. See, even me, an old physics geezer, right? Still got to watch me. But yeah, so just be aware these are some equations that we're going to use. I'm going to write these up on the next page. They won't make sense at first. Ask lots of questions. Hit unmute anytime you want and ask. Okay. Oh, and so this is the summary of how those two sets of equations relate to each other. And again, different books will use this versus that, or this versus that. And sometimes we'll use delta x, and sometimes we'll use x final minus x initial. Let's get to a problem and do something, all right? So I'm going to scroll down here. I'm going to let you do 2.1 at home. So you could try that one after this class because that's a pretty straightforward one to start up. And then I'm going to use this strategy today, and we're going to have much more time to practice this for the next 2 weeks. So just be aware, this is the strategy that is going to guide my reasoning. I'm going to read the problem, draw a picture, label it, list some crap that I know and list some crap that I don't know, list any equations that we have. I'm going to reread the question, do algebra. At the very last step, this is the thing that students who are not used to physics, notice we do not plug in numbers until the very end after we've already solved the problem. This is a big deal. I cannot stress that enough either. And then finally, this is something that maybe you don't do in your physics class, or sorry, in your math class as much. Check if the answer makes sense. This is a big step for a physicist because your answers have to relate to the real world. Yeah, is your answer reasonable? That's not something you usually do in a math class. Is it the right order of magnitude? Meaning, is it supposed to be a billion, or should it only be a million, or should it be a 10,000th? I don't know. So we'll talk. Yeah, this is not something you learn in a day. This is why physics is hard. There's not a cheat sheet. You're learning this procedure in this chapter, all right? We want to learn this procedure. Let's go practice that procedure with an example and get you the heck out of here. So let's take a look at this one. I'm going to draw this up on the board. Hopefully you've got it there, but I'm going to do this 2.1 and a quarter, okay? 2.1 and a quarter. And remember, at any time, you could talk to Jay in the chat if you want, or interrupt me at any time, unmute. Oh. I'm going to make my plane really simple. A block with wheels. All right. Okay. And so let me get my screen bigger here for the live stream. Come on. There we go. All right. So this is what I read that problem. I was looking at 2.1.4. And so I looked at this problem right here. And this is the first stuff that I wrote on my paper here. All right. The idea is I got the problem number. I drew the picture myself on my own paper so I could doodle on it. I labeled some stuff that was in the picture. So I read, I drew, I labeled. And pretty soon I need to list my knowns and unknowns. There was actually one more piece of information in there. It said something where in the problem statement, it told us that G was some number, a positive number. If you've never had physics before, you don't have any trouble with this. G is just some number, I told you. Now, one of the things that drives me crazy is students that come in that have had a tiny bit of physics and they say G is gravity. The answer to question A is G is not gravity. Okay? G is not the acceleration due to gravity. G is this official statement. G is the magnitude of free fall acceleration near the Earth's surface. And no one is ever going to say all that. They just say G is 9.8. But it's the magnitude of an acceleration. Notice it is not an acceleration. It is not a force. Gravity is a force. This is the acceleration for an object, and then you take the magnitude of it. So if you drop this marker right here like this, it accelerates. It's called free fall. So there's no other forces acting on it other than gravity. And so if you have a situation like that near Earth, the object will accelerate. The magnitude of that acceleration while it's falling is called G. And so this is a much faster way to indicate we need to use this number 9.8 than all this. Now, obviously, you've probably heard G's like, how many G forces am I feeling, etc. It does relate to all that. It's comparing the forces you feel to the acceleration caused by the force of gravity when you fall out of a plane or out of a taco truck, whatever. All right. All right. So let me get this marker. Okay, great. So that said, I think the answer to question A is now pretty obvious. It's not gravity. Let me get that back here. So A and B. It is not gravity. It is not the acceleration due to gravity. And then it is never negative. It is always positive. It's a magnitude. If you have a magnitude, this is a positive number. So I'm just trying to hammer this in. I don't know if you could tell, students end up screwing this up a lot. So G is always positive, and it's a magnitude, right? So, okay, enough said on that. Now we could get to the real question. Part D. So 2.1 and a quarter D. That stuff was all just understanding what this letter G means. How far? When I say how far, what are you thinking? What kind of units or what kind of word relates to how far? What is the thing that we're looking for?
Distance?
Distance, yeah. So it's some kind of distance question, right? Wait a minute. Do we need to watch out for distance and displacement on this question? When this plane is landing, does it reverse direction? What do you think? Go with your gut.
No.
No. So in this case, we could even say displacement, right? Because we could use them interchangeably if it's not reversing direction. But it is asking something about this. All right. So an old physics joke is you say, oh, we're looking for the distance. This is WTF. What to find? I'm sure that's what you were thinking. What to find is distance. So that's basically a way of saying, keep your eye on the prize. What are you looking for? Distance. All right. So now in this case, I'm going to follow the next stage. We read, we drew, we labeled. I'm going to identify my list of unknowns. So there's delta x, the initial x, the final x, acceleration in the x, and t. And I'm going to check if that's still on the board. It is. You might be saying, whoa, dude, where did you get that list of crap? How did you know to write that stuff down? I'll show you. This is a problem with an object moving in one dimension. I know that eventually I'm going to be using some equations that look like these. And I noticed that what I wrote down on the board are the variables that appear in those equations. These are the symbols that appeared in these equations down here, okay? And so the idea is we list them and we write down which ones of these things do we know, and then we keep an eye out for what we're looking for. And so this is probably what we're looking for, because doesn't that relate to distance somehow in this case? It's actually displacement, but because it's moving in one direction, distance and displacement are related. All right. So now I got to read the question again. All right. How far will it go? Okay. Okay. So now let's go through this. Delta x, that's what I'm looking for. That's what to find. So that's WTF. Or you could just put a question mark. Usually I get lazy and just do a question mark. All right. Jay, can you tell Travis we're about to wrap up here? I'll finish this one next time probably, but V initial X, that one is 170 miles per hour. To be honest, the first thing I would do is probably change this to meters per second before I even write it in there. Okay. And then V final X. Does anybody know what that means? V is velocity. F means final in the X direction. What value is that in this problem? I know it's time to go, but let's finish it. The setup anyways.
Positive.
I read this one. Be careful. Read the question to part D. I don't know who that was, but where are we? We're doing this one, right? Part D. Read that sentence right before the question mark. What does it say? Stop, right? What does that tell you the final speed is? Final velocity. Yeah. So this is where people hate physics. You have to read words and understand them. Oh my gosh, and interpret them. Now, you know, it's like, imagine your math class if it was only word problems. Well, then it'd be a physics class, right? So the entire class from here on out is word problems forever, pretty much. Okay. So if you don't like word problems, that's what I'm here for. I will help you like identify these key phrases in the words. Like when a physicist says these words, full stop, you're supposed to think, oh, something's got a zero velocity. You could start from rest. That would be a zero initial, things like that. Okay, and then A here is so again, it's 0.175 G. G is this number. So this shows me I should definitely convert this one. This is in miles per hour. This one's in meters per second squared. So it would make sense to get this thing into meters per second. All right. And so in this case, did they tell us a time? I didn't see anything about time in there. So I know some of you may need to go. So if you need to go, I'm not offended if you leave and take off. Since this is being live streamed, I'm going to go ahead and finish this problem out really quick and at least to the next step and then tell you how to phrase it. So we've got about 2 more minutes here. So I've labeled everything. Next, I would write out some equations. I would look at this equation and see if it works. Where did I get this equation from? From the equation sheet on the back or in your chapters. Where is it? Where is it? Right there. So here's, it looks like I wrote it a slightly different way back here. But then I'm looking at this and I'm like, you know what? I don't know what time is. So I can't do this one because I don't know what this is either. This is a great equation, but that doesn't help me. So I go to the next one. And again, these equations are listed on that page we were just looking at. I'm going to look at this one. I don't know what time it is, but I do know AX. I do know this, and I do know this. So I should be able to figure out the time, plug it in here, and get it. Not bad. But rather than trust that, I'm going to write my third of the big three. These are my 3 favorite. And I made a mistake in here we could discuss in just a second. Now let's check this one out. In this problem, I know this, I know this, aha! I could get that. That's a faster way to do it. Now, I caught myself, fortunately, just in the nick of time. One of these things has a mistake in it. Which one? And what is the mistake?
Is the second one supposed to be t squared?
Nope. So this is a speed or a
Oh, I thought you were talking about the formulas. Oh, never mind.
Oh no, the formulas are okay. It's in this table. There's something wrong with this table. One of these things is not like the others.
Is it AX?
Yeah, what's wrong with it?
We have to multiply it by 2 or
Nope.
man.
It is a sub x. It's this green one. Something's wrong with this one.
You forgot the units.
Oh, go ahead. Not the units.
Should it be negative?
Yeah, who is that?
Me.
Okay, I don't know who that was, but yeah, why should it be negative? I guess that's what I really want to know.
It's because it's slowing down to a stop. So
yeah, nice. So look, do you agree in this case, it's moving forwards and then it's going to slow down? If acceleration is a positive number, wouldn't it speed up in this case? Bad. So we need a minus sign right here.
Quick question.
Yes.
So in a word problem, the keywords like slows to stop, that means that the acceleration is going to be negative?
It means acceleration will be opposite the sign of velocity.
Okay.
And let me show you what I mean. So one of the things that, this is actually the last bit of that page we were looking at that I said I would cover on a future date. So for objects that are moving to the right, you're absolutely right. But what if an object's moving to the left? If you're moving to the left and your acceleration is negative, wouldn't you get faster and faster going to the left? And so that's where we have to be careful. Non-physicists will say the term decelerate, and they'll think that is a negative acceleration. But generally speaking, it's better to think of acceleration as a vector. And this little piece right here. So if you see these words right here, I'm looking at this table. If you want to be moving forwards and speeding up, A and V are both positive. They're both greater than 0. If you're moving forwards and slowing down, that's the case we were looking at. Velocity is positive and acceleration should be negative. But look at these two when you're moving backwards. They get flipped. Why? Because the velocities have negative signs in them. So then the accelerations need to have the opposite sign to have the same effect. I don't know who that was, but did that start to address that question?
Yeah, it helps. Thanks.
Yeah. And so at this point, you're probably ready to read a book and get a lot out of reading the book, right? We didn't. Yeah. So I'm going to go ahead and stop the live stream really quick.